section. But I think in this new book, they put it kind of with the acid-base chapter, which I guess it sort of goes with, I suppose. So we're just going to talk a little bit about this just to obviously expose you to it here. It's not necessarily directly related to acid and bases that we deal with in this class. It's more related to kind of solutions, actually, which is why it's usually kind of in that chapter, or like the reaction chapter. But we'll talk about it here now, if there's kind of no questions on some other stuff. So technically it is sort of in, I guess, the acid-base chapter in this new book, but it's a topic known as Le Chatelier's principle. And I'm just going to kind of sketch all this stuff up here. Sketch all this stuff. I'm going to do some wonderful drawings, I suppose, on here, which is usually what we do. Le Chatelier's principle is this sort of idea, which, like I said, really does sort of involve sort of solutions and types of solutions and sort of what happens. And it really involves sort of certain types of reactions, and involves reactions that are similar to what we talked about when we talked about weak electrolytes. And weak electrolytes, if you remember, had those reactions where we had, or those arrows, where we had kind of those reversible arrows. So in a sort of equilibrium reaction, which is what is sometimes referred to, you'll have those arrows heading in both directions. And I think as we talked about when we were talking about sort of electrolytes and stuff like that, what those arrows represent is, this is what is referred to as a reversible reaction. And when we have a reversible reaction, what that means is the reaction could head in the direction of the reactants to products. And that's what is sometimes referred to as the forward direction of this reaction. So kind of normally how we think about a reaction happening, going from reactants to products, that's sort of the forward direction, or sort of, you know, what this arrow right here kind of represents, the top arrow. Now, in these type of reactions, what happens is at some point, you get enough products that have been made that they decide, hey, we kind of want to go in the other direction, where we get kind of products that decide we're going to go back to reactants. And that is sometimes referred to as the reverse direction in this type of reaction. And that's what I kind of scribbled over there, the bottom kind of arrow represents. So that's why we kind of have these two arrows, one representing the forward direction, you know, heading towards the products. Once we achieve really enough products, the reverse reaction can happen. And you could write something which is referred to as the equilibrium constant, which is capital K. And for any reaction that basically is reversible like that, you can kind of write what's known as the equilibrium constant. And it is really products over reactants. So for example, if these little, there we go. The little letters are the coefficients in the balanced equation. The way we do the equilibrium constant is we take the products, the concentration of the products to their exponents, divided by the concentration of the reactants to their coefficients as the exponents. And it's an equilibrium constant, which means for a given temperature, it's going to remain relatively constant. It won't change. But what does it mean when we reach chemical equilibrium, which is really what we're talking about in these type of reactions? So whenever you have these reversible reactions, we could reach what is known as chemical equilibrium. And sometimes people misunderstand what equilibrium means. They think, well, equilibrium means that they're equal on both sides. We have the same amount of reactants as we do products. And that's what kind of makes sense equilibrium would mean. And it actually doesn't mean that. So when we talk about a reaction that really reaches chemical equilibrium, what we're really talking about is actually the rate. And we're talking about the rate of the forward reaction will equal the rate of the reverse reaction. So what does that mean? It means just as quick as it goes this way, everybody's coming back the other way just as quick. So just as fast as the reactants make products, those products will go back and make reactants. So what does that mean? It means when you reach chemical equilibrium in that situation, wherever anybody is at that point, they're going to kind of lock themselves into place. So for example, let's just say we reach chemical equilibrium in this reaction. And again, just hypothetically speaking, this guy had 2 molar in terms of his concentration. This guy had 4 molar. This guy had 3 molar. This guy had 6 molar in terms of his concentration once we reach equilibrium. Because the rate of the forward reaction equals the rate of the reverse reaction, they will maintain those concentrations over that period of time unless you do something to screw it up. And that's what we mean by chemical equilibrium. It doesn't mean that we have the same amount of reactants and products. It just means as fast as it goes from reactants to products, or the forward direction of that reaction is just as fast going to come back the other way. And again, it's kind of like a balancing act at that point. Since it's kind of going back and forth at the same rate, everybody sort of locks into place where they're at. Any questions on sort of what equilibrium means? Now, you might wonder, have we ever seen a K value? And we actually have in this chapter, the acid-base chapter, that Kw is an equilibrium constant value. And that's actually what that Kw value is. And that's because when you look at the reaction of water as it breaks apart into H plus and OH minus, you could write your equilibrium constant, which is your products divided by your reactants. But there are 2 things that do not go into here. Anything that's a liquid or a solid is not included. So that's why we wouldn't put anything there. And that's actually how we get our Kw expression, because water is a pure liquid, it wouldn't be included. And again, that's really what the Kw is an equilibrium constant. It's a reversible reaction between water and basically H plus and OH minus. That's essentially what's happening in a solution. You know, you got water in there and you got some H plus and OH minus floating around and kind of going back and forth at the same rate. At some point, it will sort of reach equilibrium and we'll have a certain amount of each of those guys in there. And at neutral solution, it would be 1 times 10 to the minus 7 of each of those guys in that particular solution. Any questions at a equilibrium reaction? Again, that's what these are sometimes called, a reversible reaction. Basically, they will reach equilibrium when the rate of the forward direction equals the rate of the reverse direction, essentially locking everybody into their concentrations. And they're going to be very happy at that point. Any questions on any of that stuff there? Now, what we're actually going to talk about, which is Le Chatelier's principle, is what happens when we get this system that's at equilibrium, and then we screw with it basically and mess around with it and mess it up. So we do something to the system that's kind of nice and happy. It's moving at a nice rate forward and backwards. It's reached chemical equilibrium. We're basically going to do something to this type of reaction that's essentially going to mess it up. And when we mess it up, this principle, which is known as Le Chatelier's principle, will make the reaction sort of go either to more products, more reactants, in order to get back to equilibrium. So when we talk about Le Chatelier's principle, what we're talking about is we have a system or a reaction that has reached equilibrium. And again, what that means is what we just talked about, that rate of the forward direction will equal the rate of the reverse direction. Everything's going back and forth at the same rate. And then we do something and add a stress to it. So we kind of stress out the system. What that's going to do is essentially mess up the equilibrium. And it's not going to want to kind of remain that way. The reaction itself is wanting to sort of correct itself. to get it back to equilibrium. So it's going to then correct itself to get back to equilibrium. And the way it's going to be able to do that is typically three things. It will either shift to the right, which means it will need to make more products. It will either shift to the left, which means it needs to make more reactants. Or the third thing, which I guess really doesn't do much, is it will actually cause no change to occur. It won't go either way. So these are three things that the system will try to do in response to some type of stress that was added to it. So you again have sort of the system that's kind of happy, it's at equilibrium, then you kind of stress it out. It wants to get back to equilibrium. And in order to do that, it needs to either make more reactants, more products, or there might not be anything that can be done for that situation. So what are the stresses that we can do to a system? Well, we can do something with concentration. And typically with concentration, we could either add or remove concentration. We could also do something with volume and pressure. We could also do something with temperature, increase or decrease. Same thing with these guys. You could either increase or decrease these guys. Or we could add a catalyst. A catalyst is not a reactant. I think we talked about this when we talked about reactions. It's not a product. It is there simply to speed up a chemical reaction in most cases. So we're going to talk about each of these things and sort of what happens when we have a system at equilibrium. So let's first start with concentration and sort of what happens in that situation. So with concentration, you essentially can either do one of two things. You can add more. And when we add more, what ends up happening is it will shift away from the side we added it to. So when we talk about adding more to one side or the other, in reality, if we have all this stuff in a beaker or a test tube, whatever it may be, there's really no left side, right, or right side. There's really not. But what we're talking about is the actual equation. Left-hand side would be the reactant side. Right-hand side would be the product side. So when we talk about left to right, we're talking about adding more reactants or adding more products. That's what we're essentially talking about here. So whenever you add, it goes away from the side. So AA is a good way to remember that, add away. And the other thing that we could do is remove concentration. When we remove concentration, it always shifts towards the side that we removed. So adding goes away, shifting comes towards the side we removed. So let's talk about sort of what happens here. So we could do a wonderful sort of system here at equilibrium, like a teeter-totter type of thing here. Award-winning stick figures here. We'll call this guy over here reactant side. We'll call this guy the product side. We'll go advanced stick figures and put faces on them. There we go. And we'll say this guy is at equilibrium right now. So he's at equilibrium position 1, if you will, which means we're going back and forth at the same rate. Everything's good. So what happens if we decided to add more products? So somebody decides to hop on the product side of this sort of teeter-totter. What's going to happen in this case is some situation like this. And these guys are probably happy, maybe. we've now really messed up the equilibrium, right? We were nice and at equilibrium. We added more products, really kind of messed up the equilibrium. What needs to happen to sort of right the ship, if you will? What needs to happen is we actually need to add more reactants away from the side at which we added. We need to put more people on the left-hand side of this teeter-totter. And if we do that, we will once again get back to equilibrium position 2. So this is what happens in a situation where we add more concentration. We added more to the product side. It messed up the equilibrium, which is the middle picture. To fix that, we need to put more people or make more people away from where we added. And we once again come back to equilibrium. Any questions on that there? All right, so my once a year artwork here. Let's go back to our original equilibrium here. Again, this guy being our reactant. This guy being our product. Now, and again, we're at equilibrium here to begin with. What happens if instead of adding more people to the product side, this guy decides, I'm hopping off. We're going to remove some products. Well, if that guy hops off on the right-hand side, what should happen is the poor guy on the left-hand side should find himself now probably slammed into the ground. Again, not so happy in this situation. What do we need to do to fix this situation? Well, we obviously need to put more people on the right-hand side. So we actually need to shift towards the side that we removed. That's going to, again, if you want to think about it, right the ship. And it's going to return us to that nice equilibrium position where everybody is happy at this point. Question on that. We learn a valuable lesson. Don't be on the left-hand side, obviously, of the teeter-totter, not a good deal. But more importantly, when we add, it goes away. And when we remove, it goes towards it. Any questions on concentration there? So let's say we had this equilibrium reaction of 2A plus B goes to 4C. And let's say we added some C. Let's say we removed some B. And let's say we added some A. Take a moment here and decide, will it shift to the right? Will it shift to the left? Or will there be no change? So take a moment here for each of those and think about what will happen. Okay, so let's take a look. So first off, we're adding more C. So when we add, it goes away. So that's a good way to remember it, add away. So what are we talking about away? Well, C is on the product side. So if we added more C, that would be like adding more products. It would then shift away from that side and actually would shift to the left-hand side. Why is it really doing that? When you add more C, you're adding more products, which means all those products don't have to go hunt around to find people. There's a lot of products there. And that really kicks off the reverse reaction in this case, which is why it shifts away from it in this particular one. Any questions on that? Then let's take a look at the next one, which is, in this case, we're going to remove B. So again, here we want to think about where B is at. B is over here on the left-hand side. When we remove something, it actually goes towards the side we removed. So in this case, it would actually go to the left as well. heading towards the side of the equation that we removed it from. Any questions on that one there? Okay. Why does that happen? Well, when we remove some B, the left-hand side is really deficient. And the product side is going to go, oh, we need to make more reactants. So that's going to kick off the reverse reaction from actually occurring in this case. Lastly, here we're going to add some A. Again, when we add, we're going to shift away. So A is on the left-hand side. Add away, which means this reaction would shift to the product side in this case. Again, we have more reactants. Because there's more reactants there, they're able to react a lot quicker. That's going to force the forward direction to occur a lot faster and cause it to shift to the right. Any questions on concentration or any of those three there? Okay. So that's one stress that we could do to a system that's at equilibrium, is really play with the concentration. How do we add more? Adding is pretty simple. You go to the shelf, you pick up the bottle and you dump it in. Pretty simple. Removing something, we don't reach in to remove it. There's really kind of two ways to remove something, and removing basically can be accomplished by making a precipitate. So you make a solid that forms, and that solid essentially takes something out of the solution or the reaction. Or you can make water. And making water when you have H plus or OH minus is a very common way you could remove H plus or OH minus from solution. Why do these two things do that? If you remember earlier, the two things that are not included in the equilibrium as a solid are a liquid like water. So when we make these things, we're kind of removing them from the equilibrium. And that's why these two things are two ways that we could kind of remove something from solution. Obviously, you can't just reach in and grab an ion that's floating around in the solution. You have to kind of take it out in these two forms. Any questions on that? All right, the next kind of stresses that go in a Le Chatelier's principle are kind of related to each other. It is volume and pressure. And if you remember, these two things are related to each other through our gas law, and that's our Boyle's law. And if you remember, the relationship is as the pressure increases, the volume will decrease, and vice versa. As the pressure decreases, the volume will increase. So in this situation, if the pressure is increased, that means that the volume is decreased. So what's really happening here, as we squish the volume, the gas molecules in an equilibrium reaction are now in a very small volume. That's going to cause a lot of collisions to occur. That's going to cause the pressure to start to go up. To fix that, so sort of the change that's happening is pressure is going to start to rise. To fix that, we need to shift to the side with the least number of gas molecules. That is obviously reaction dependent, but the idea here is because we shrunk the volume, if we put less gas molecules in that small volume, the pressure should kind of come back down to sort of equilibrium pressure in that case. Opposite would be true if the pressure started to decrease, started to go down. That's a result of the volume increasing. So in this case, we're making the volume bigger. So the pressure starts to drop. So to fix the pressure coming down, in that big volume, we actually need more gas molecules flying around. More gas molecules flying around will cause more collisions and cause the pressure to come back up. So we'll shift to the side with the most number of gas molecules. Again, it does depend on the actual reaction that you're looking at. Personally speaking, when I think about pressure and volume and they're related to each other through a gas, I personally think about the volume and keep it very simple that in a smaller volume, I need less gas molecules. In a larger volume, I need more gas molecules. And that's the way you kind of want to think about it. So for example, we looked at our same sort of guy that we were looking at there before. So if I decrease the volume here, if I increase the pressure, take a moment and think, will it go to the right? Will it shift to the left? Or will there be no change based on this reaction? So take a moment and we'll talk about it. Look and see how we can kind of go after this one. First one, we're decreasing the volume. When we decrease the volume, that means the pressure will really increase in that case. But really, the volume's a good one to look at. When we have a small volume, we want less gas molecules. So we do need to go to the equation, look at everybody that has a G on the left-hand side, count the coefficients. That's a 2 and a 1. So that's a grand total of 3 gas molecules there. We then want to do the same thing on the product side. That's a gas molecule coefficients of 5, which means we have 5 gas molecules here. So based on this equation, when we decrease the volume, we want less gas molecules. That means in this case, it does need to shift to the left-hand side towards the reactant side. Question on that. Again, originally decreasing the volume is going to cause the pressure to start to jump. By lowering the number of gas molecules, it will bring the pressure back down and come back to equilibrium. Any questions on that one there? If we increase the pressure, it is actually going to do the same thing. It's going to decrease the volume. So we're actually going to get the same result in this case. So they are tied to each other, pressure and volume. Now, if we actually increase the volume, the opposite would be true. If we increase the volume, the pressure would go down. In that bigger volume, in this case, we would need to go to the product side. Any question on pressure and volume related to just gas molecules? And again, the easy way to kind of think about it is volume. Large volume, more gas molecules. Small volume, less gas molecules. And that's a really good way to do it. And it does depend obviously on the reaction you're dealing with as to which side has more or less gas molecules. So you simply just need to count up everybody who's got G's and their coefficients, and that will give you the totals that you need. Any questions on that one? Okay, so we talked about volume and pressure. We talked about concentration. The last really major stress that occurs in a system that's at equilibrium in Le Chatelier's principle is temperature. And temperature works the same as concentration. And what that means is if you increase the temperature, it will shift away. And if you decrease the temperature, basically throw it on ice, it will shift towards. Now you may be asking, which way is it shifting? Away and towards what? And temperature really involves the type of reaction that you're dealing with. And the type of reaction is whether it's exothermic or endothermic reactions. So as a reminder, let's talk about what those reactions mean. When we have a endothermic reaction, that means that heat and energy is absorbed. It is represented by like a delta H value that is positive, a Q value that's positive. That's the enthalpy I think we talked a little bit about earlier on in the semester. And Q is heat, we also talked a little bit about, but basically positive values for energy is given that. What does that mean when you write it into a reaction? When you write it into a reaction, the heat or temperature is thought of as a reactant, like it's being added. So it would be on the reactant side, which means if the reaction is endothermic and you increase the temperature, it would be like adding more heat and stuff to the reactant side. It would shift away and shift to the product side in that case. If you decrease the temperature in an endothermic reaction, that would be like removing heated energy or removing reactants. And when we remove reactants, it goes towards the side we removed it. It would cause it to shift to the left-hand side. Any questions on that one there? So what happens if the opposite type of reaction occurs, which is a exothermic reaction? Exothermic reaction means that heat and energy is released. In terms of delta H value, that usually is a negative number. Q value, that is a negative number as well. And what does that mean in terms of the reaction? Well, in terms of the reaction, A plus B goes to C. Heat and energy would be considered a product in an exothermic reaction, which means if you increase the temperature, that'll be like adding more products. And when we add, it goes away from the product side and it would shift to the left. If we decrease the temperature, like throw it on some ice, that would be like removing heat and energy, which in this case is on the product side. And just like concentration, it would go towards it and it would go to our product side. So temperature basically depends on whether or not the reaction is exothermic or endothermic. And that's basically one of two ways which you'll be able to determine that. Either they will actually write heat on one side of the arrow or the other. They may even actually put a number value like, 175 kilocalories actually on in the reaction or something like that. Or they may just give you the reaction and at the end write something like the delta H equals plus 175 kilojoules. The number doesn't really matter. The plus matters, meaning endothermic, or like the delta H is equal to minus 175 kilojoules. Again, number doesn't really matter. The negative sign is what matters to determine whether or not it's exothermic or endothermic. And then it basically works the same way as concentration. If you increase the temperature, like putting it on a hot water bath, it's going to shift away from whichever side has the heat and energy. And if you put it on ice, it's going to remove the heat and energy and go towards that side. Question on temperature. Now, the very last thing in terms of Le Chatelier's principle is if you added a catalyst. And a catalyst, as I mentioned earlier, is not a reactant. It's not a product. It's there to speed up the reaction. It doesn't get used up in the reaction either. If you add a catalyst, it will cause really no change to occur. Also, if you add something like a noble gas, since noble gases pretty much are chemically inert, it also will not cause any type of change. So it is possible to get a no change situation. Catalyst is a common way that that's occurred. It will just get you to equilibrium faster, but it will not cause it to shift one way or the other as a result of adding a catalyst. Any questions on Le Chatelier's principles there? All right, so let's finish up by looking at a couple examples here, and I'll just give you a variety of ones to do. So we'll do this. Let's look at this reaction here. And let's run through a bunch of things here. Let's first start with it. Let's say it is exothermic, this reaction. Our delta H is negative. All right, let's say what happens. Will it shift to the right, to the left, or no change if we, let's say, add NH3 to it? remove N2, increase the temperature, decrease the pressure, add more H2 to it, and add a catalyst. All right, take a minute or so here for each of these. Determine, will it go to the left, will it go to the right, or will there be no change? Okay, so let's take a look. So first off, since it's exothermic, that means heat and energy is released. And what that means, a good thing to do is just kind of put it in there. That means that heat is really a product in this case, like it's being given off. So that takes care of what this means. Now let's talk about adding NH3. So NH3 is a product. When we add, it goes away from the side we added it to. So that should cause the equilibrium to shift to the left in this case. Any questions on that one there? We're then going to remove N2. So N2 is a reactant. When we remove something, it goes towards the side we removed it from. Also going to cause this equilibrium to shift to the left. Now we're going to be increasing the temperature in this case. So increasing the temperature means that we are going to be adding more heat and energy. And since we already determined that heat is a product, when we add heat and energy, it should shift away from it, and it would cause it to also go to the left in this case. The next one is decreasing the pressure. When we decrease the pressure, that means volume-wise, the volume should increase. So that's an important relationship. Since the volume would increase, left-hand side, we have 4 gas molecules, 1 here and 3 here. Both of them are G's, is gas. Right-hand side, we have 2 gas molecules, 2 here, on a guy here. That means we want to go to the side with more gas molecules. In this case, we'll also shift to the left. Any questions on that? Adding H2. H2 is on the left-hand side when we add away AA. So since we added to the left, it will cause the equilibrium to shift to the right. And lastly, here we add a catalyst, which will cause no change to occur. Any questions on any of those there? Okay, so that is basically Le Chatelier's principle. It is in this new book, actually in the acid and base chapter, kind of in there with acid and bases, but you do need to know, obviously, questions like this, if you change the concentration, change the temperature, change the pressure or volume, you know, which way will it go? Will it shift to the left? Will it shift to the right? Will there be no change? Any questions on any of those there? Okay. So then I guess we'll officially wrap up the acid and base chapter. We will roll into actually on Wednesday some organic chemistry.